I'm going to talk about something that builds off of the previous talk. And it's a bit surprising, that took us by a lot of surprise, and hopefully you'll find it interesting. And that is how neurons respond to virtual reality. And the second part is, why should you care? Care a lot, actually. So as you know, we have spent a lot of time in this meeting and elsewhere worrying about the optics. But at the end, the image that comes into the eye is inverted, the two eyes images are mixed together, and there's that giant thing in the skull that's interpreting the whole thing. And how is that doing it? How is your brain responding to VR? Not your mind, which comes from the brain. And you can talk about it to say, I see the image distorted, or the image is clean or not clean. How do neurons respond to virtual reality? Individual ones. And there are lots of neurons in your brain. So which neuron do you look at? In human brain, there are 100 billion neurons. So which neuron should you look at? And how do you even make sense of it? Because it's these neurons which are making sense of whatever you're seeing. So that's why I'm doing this. I happen to be in the Department of Physics and Astronomy. We look at stars sometimes look at quantum particles, and we do neuroscience too. And the work is done thanks to this wonderful sets of people whose names you will see if this thing doesn't cut it off. So let's get started. So how does our eyes or our senses see anything at all or feel anything? And the basic idea is this, that you have the light in case of the eyes that comes into the eyes, then it goes to the brain, literally at the back of the brain, and somehow, we're going to wave hands there, generates perception. Wait a minute, what happened there? What is that perception? And then from perception you get memory. And that's when you say you had a good VR experience, a bad VR experience, or you didn't like it. So that's that thing, and that's not so simple. So we have some ideas about light going to eyes, so I'm going to skip that. And let's get into the brain part. So the human brain, right there, it's a picture. It's only 1.5 kilos, 3 pounds for those who don't know kilos. Pretty small, about that big. And it's only 1/50th of the human body. Doesn't matter how big the head is, it's pretty tiny. But still, 1/3 of all the known diseases to humans are in the brain. 1/3 of all the named diseases. And the volume of neurological diseases keeps growing every year. So a lot of stuff is going on there that you don't know. So what's inside the brain? Inside the brain you have neurons, about 100 billion of them. In the human brain, you're carrying 100 billion neurons, and this is an image of one neuron, that's the image of other neuron. And these neurons, apart from having interesting shapes and so on, do something very different than what you yourself are aware of. So your mind is completely unaware of what your neurons are doing. And I'm going to play this to you, a live neurons activity, and I'm going to challenge you to tell me that that's what you hear. Now, before we go there, what makes the brain special is not only there are 100 billion neurons, these neurons are connected. So there's neuron number 1, that's neuron number 2, and they have a connection called the synapse. And each neuron has 10,000 synapses. So each neuron, whatever it says, it broadcasts to 10,000 other neurons. And each of these neurons in turn is listening to 10,000 different neurons. So these are ideal Twitter guys. They listen to 10,000 other people, and they broadcast everything they say to 10,000 totally different sets of people. So very different language than what you and I are used to. I speak, you listen, you speak, I listen. That's not what your neurons do. That's what neuron does. So what happened there was a neuron, and somebody did an experiment where they simply moved a bar of light in front, back, and forth. You're supposed to see a bar of light. You go to the eye, go to the back of the eye, there is still a bar of light. And this is so interesting. I'm going to play this again. Watch this. And that's an oscilloscope. There is no bar of light. You see some burst there. You see the little spiky little thing, and if this thing works, I'm going to try to pause this, but most likely it will not work. Nope, it doesn't work. So what happens is that every time these spiky little things go by, each neuron, whenever it speaks, it generates a burst called a spike. It looks like a spike because it's very thin. So neurons generate these spikes. Even in your eye, the photoreceptors come in, they activate those neurons, which are photoreceptors, and out come spikes. The spike lasts only 1 millisecond, a thousandth of a second, and they are 100 millivolts in amplitude. So everything that goes on in the world outside, whether it is light from the eyes, or sound through your ears, or touch on your screen, on your skin, or taste from the food, everything is turned by neurons right at the periphery into that language of spikes. And the currency is the same. Whether you go into the ear, the hair cells, underneath your skin, all those transport guys are transforming everything that's coming out from the outside of the brain into a language of its own in the brain called spikes. And then the brain takes over. It starts to use that language, not the language that we are used to. Neurons now represent information using the same spikes. More spikes, stimulus A, less spikes, stimulus B. Neuron A fires more spikes, there is stimulus A. Neuron B fires more spikes, there is stimulus B, and more complicated stuff. That's how information is represented. And then comes even bigger surprise, which makes the brain really special, which is that this connection between the neurons are very, very intricate. There are fat books written about it, and still we are understanding it. And the most important thing to take away is that every time a neuron fires a spike, the connection between neurons changes, unlike your computer, whose clock speed is much more impressive than a neuron. A neuron's clock speed is a kilohertz. This thing is 2.5 gigahertz. But what a computer cannot do yet is what neurons do, that every spike changes the connection. And those connections between neurons are sensitive to the timing of spikes within a couple of milliseconds. And it's not just 5 or 10%. If there are two neurons with the spike timings were X, the connection of the synapse can increase by 100%. If the timing changed by just a handful of milliseconds, the synapse connection changed by minus 100%. Huge effect. And we'll see what that does when the animals are in virtual reality and how that changes the brain maps in a fundamental way and why we should worry about it. So that's what goes on. Once the information goes from here, these guys are generating spikes of all kinds. And then there is one more thing we got to worry about, apart from neurons and synapses, are the circuits in the brain. So this is right there is a retinal ganglion cell, right at the back of your retina. And these, each different colored boxes, I won't tell you what the names are, because I don't even know the names. There are so many of them. There are hundreds of brain areas. And all the way at the other end is this tiny little thing called HC, hippocampus. That's the part of the brain that is creating the perception of immersion. That's the part of the brain that's telling you you are in a virtual space versus you are looking at a TV screen. That's where the magic is. So you got to go through all this in next half an hour. No, I'm kidding. We're not going to do that. We're going to jump right back at that. And we are going to see what do individual neurons in the brain that create the perception of not just photons, but perception of space and memory. What are they doing in virtual reality? So hippocampus is actually a pretty funky structure. It's right in the middle. So it goes from the eye, bypasses it, goes here, goes up there, and then the information comes into the hippocampus. And it's a part of the brain that's very special in many ways. First and foremost, hippocampus is this one part of the brain that does two very important things. One, it creates maps of space. So you figure out where I am in the virtual space. That's what your hippocampus is doing, telling you where you are. The second thing hippocampus does is it makes memories. Not just memories of where you are in space, but even a memory of this conversation. So if you heard the word hippocampus just now, And if at the end of the day, when you had enough beers and somebody asked you, what was that random guy talking about? And if you produce the word hippocampus, that information is stored in your hippocampus. That's what happened. And the way that information got stored in hippocampus is that some synapses, a lot of synapses in your hippocampus change permanently. So I'm rewiring your hippocampus right now. It's true. Totally true. That's happening. Every little experience changes hippocampus. Now, unlike the circuits in the eye, where we have to worry about children, where the circuits are getting set when we are growing up in first few years, hippocampal circuit remains plastic all the way till you die. So every experience you have changes your hippocampus permanently all the way till you're dead. So this circuit, which creates memories and perception of space, is changing constantly. In fact, it's changing so much that even when you go to sleep, this circuit is doing something fascinating. We are not going to get into that some other day. And unfortunately, that very delicate part of the brain is hit by these major diseases: Alzheimer's disease, most kinds of epilepsy, post-traumatic stress disorder, depression, schizophrenia, and the list is long. So you got to be careful with that part of the brain. If you do funny things to it, I don't want to tell you what might happen. So we are going to listen to one neuron in hippocampus when there is a rat that's running around in the world, and we're going to figure out how is the rat's hippocampus creating map of space. So I'm going to set this up for you. What's going on is that there is a room, a real room, with these 4 different walls. And in the middle, there is a platform that's 2 meters diameter. And there is a tiny, tiny electrode set in the brain. The electrode is 100 times thinner than human hair. So it doesn't damage the rat, not too much, unless 100 times thinner than hair you think is too much. And he can run around freely. And all he's doing is he's running around, and there is chocolate rain. The experimenters are throwing bits of chocolate randomly. He's just going around like a vacuum cleaner, picking up bits of chocolate. But unknown to him, the fact is that no matter what you do in life, there is always space, and there is always time. So his brain, even though he may not be required to pay attention explicitly, we make sure he's not paying attention to space. His brain is going to keep making map of space all the time. And that's what is happening in your brain too. So let's get started. So here's a rat that's going to start walking in the virtual world, and he's just walking randomly. And this discovery was made in 1973, got the Nobel Prize 2 years ago. So that's the rat, and that's its trajectory, and each crackle is 1 spike. So I'm going to shut up and let you listen. This is actual data. And we're going to speed it up. This is not how fast the rats run. So what you can see is that he was going around all over the maze. And he went here, he scratched himself, he ate a piece of chocolate here, he went there, he stood up, he groomed himself, did a bunch of things. But no matter what he was doing, this neuron was active pretty much only here, nowhere else. Pretty remarkable. So this neuron has a map of space. And of course, one neuron does not have a map of space. In hippocampus, you have about 500 million neurons. So between them, the whole map is spanned. In fact, the map is so precise that if I had the activity of only 100 neurons out of 1 billion, I can tell you with about that much accuracy where is the rat in space. Better than what rat himself can do or what you yourself can do. So a remarkably precise map of space exists in hippocampus, so precise that it's better than what you can consciously perceive. Why is that map so precise, better than what you can perceive? We don't know. We have ideas, but we don't know. So the question is, what is that map? If we understand it, we'll understand how the memories are formed, because the rat came to this crazy world first time, so he has formed memory of that map. And the classic idea has been, since the 1973, which got the Nobel Prize last year, is that if there was a neuron, and the neurons even have name, they are called place cells, because they seem to care for a place. That's how powerful the finding is. So if there is a place cell or a neuron that's active here, the idea is that that neuron is active here because it's getting some kind of input from this wall and some other kind of input from that wall. And each place that he goes into, there is a unique configuration of visual cues based on wherever he's in the room. So if you are here, you see that screen far away and the speaker to my left. If I move just 2 steps away here, the speaker is closer and that screen hasn't moved. So I can map myself where I'm in the room based on visual landmarks. That's the idea. That's why most of the virtual reality systems that we are developing, we focus on the visual cues. We don't care for anything else. We don't care for the virtual floor, how rough it is, how smooth it is. We don't care for smells or the smells coming in. And yes, you can form a perception of space sitting here based on how far it is. But if at this very moment there was the slightest smell of pizza, you're not going to figure out what I'm saying. Your head will go to pizza. Or the smell of something burning. You'll immediately form a different sense. And you have that idea all the time. If you smell pizza in your kitchen, you're fine. If you smell pizza in your bedroom, I don't know. If you smell soap in the kitchen, that is in the shower, so there are all these memories. So how is that hippocampus doing it? And by the way, the hippocampus gets input from everything. So we wanted to figure this out. And when the rats are running in the space in the real world, we can't control anything. Because as soon as it takes one step, everything changes at the same time. The texture on the ground changes, the visual cues change, the sound changes, his memory changes, so everything is linked. So we thought, hey, let's make a virtual world where we can control that when he walks in the virtual world, only the visual cues tell him where he is, and he should be able to make a map. Why not? Seemed like a simple idea. So that's the virtual reality. There is a giant ball that is drawn to scale. There's a rat here. He's sitting in a very comfortable harness. It's like, a couch potato if he were to be, a lazy boy. Even better than lying back, you can lie in a hammock swinging. Your hands are on the ground, and when he moves his paws, the ball rotates, it's floating on it, so even though the ball is big, so that it's locally flat and it doesn't feel like he's on a cliff. This movement is picked up by these sensors, goes to a computer that generates a custom algorithm for VR, goes to a little mini projector here that sends to this mirror that projects the image all around him. And we have kept the intensity intentionally low because these guys are nocturnal creatures. If you make it very bright, it's like going outside in the world right now on a summer day with looking at the sun. They can't see anything. So this is hard to see. What I'm going to do is turn this thing all for you, just now for you. And the camera is outside. The images are distorted, so they look undistorted from where he is. And even though this is pretty crummy, you can see you get a pretty decent kind of perception of stuff coming at you. And we're going to look at that a little better. If anybody has control to turn off these lights, that will be awesome, because these pictures are dim. But if nobody can do that, that's okay, we'll keep going. So that's the VR. We can have sounds, we can have lights. His movements directly control this. And because he's in VR himself and walking around, when he turns around, there is no VOR reflex issues. The rat's eyes have only one focal length, 50 centimeter. The screen is at 50 centimeter. So we don't have to worry about the focal length adjustment. The 2 eyes are on the side of the head. The binocular region is very small. So we don't have to worry about vergence correction. So many of these issues that we worry in the human brain, such as VOR, reflex, focusing, and all that, those are not issues. And as soon as he turns somewhere in the world, he can see a different thing, so there is no delay. So this is pretty much as good as it gets, and even better. In the virtual world, I will show you the rat's images. He can even see his own shadow in the virtual world. He's completely immersed, which is very hard to do in current virtual reality where you can see your own hands move. He can do that too. So let's get started. So that's a rat. There's a little bit of a reward tube in front. We wanted to make the virtual reality as good as real, so there's a soda tube in front. It gives out bits of soda, it's sugared water. And he has to go underneath these pillars to get the reward. Watch his eyes. He's checking this out. And he goes, pillar, soda, learns that. Now we want to see how well this is, so the pillar is behind him. Watch what he does. He detects the virtual edge. purely based on vision and goes there. And the virtual is determined purely based on motion parallax. Is that clear? So let's do that once more. So he's working on a virtual platform which is about 1 meter away from the virtual ground. Two of them have different texture. Once again, pillar is behind him. He goes there, sees that edge, he turns away, finds the pillar, gets the reward. All right? So he can do this for quite some time. And we have posted these videos online on this paper as well on the lab's webpage. So you can see he can behave happily, he looks around, doesn't seem particularly unhappy. And you can monitor the activity of these neurons quite well. For a long time, you can see once again he avoids the edges. So he's able to act on this virtual reality very, very well. And then we want to make sense of this data. So let's get started with equation 1. I'm not going to do that to you. You got to do a little bit of that. And then you do a little bit of other stuff, such as record the activity of hundreds of neurons, not one, but thousands of them. And here are the results. So what we do is these very thin electrodes, they can pick up activity of not only one neuron, but hundreds of neurons at the same time, so we can monitor not only what neurons are doing, but how they are talking to each other. So many neurons at the same time. So each of this ellipse is one neuron's activity, and each tiny blue dot is one spike. So there are thousands of spikes here. So this is when the rat was running in the real world. So we made a real world which was just like the virtual world. Same visual cues, same platform, same rat, same neuron. We want to now see, is the neuron, is his hippocampus and all the neurons responding to the virtual world exactly the same way as the real world or not? Because if it does, then virtual reality is working well and you don't have to worry about it. If it doesn't, you got to worry. So RW stands for the real world. And what you see is that lots of neurons are active in the real world. Each ellipse is a different neuron. This is the same electrode in the virtual world. Same rat, same day, within half an hour. And what you see is that 60% less neurons are active in virtual world. That's a whopping effect. Yeah.
Virtual reality come afterwards?
We did both ways. We did before, we did after, we waited for 2 days, some rats and only in virtual world for 1 month, and then the real world didn't make a difference. Might be small difference, but 60% is a huge effect, didn't go away. So you saw his behavior, you saw the VR, seemed to be fine, never threw up on us, rats can't throw up, and still 60% less neurons are active. In fact, we wanted to check, is he finding virtual reality unpleasant? So we'll take the rat near the VR shell, and we wanted to see, does he like it or not? And this was real rocket science, which is, will he jump or not? Will he jump into the VR shell or will he jump away? And every single day, he jumps into the VR shell. Maybe because he likes soda. You don't know. So he does that every single day. He goes in there, runs very well, and still 60% less neurons are active. Now, you can say, well, what is 60%? Is that a big deal? What I can tell you is that from, 20-odd years for which I've been studying, I've never seen any manipulation that anybody has done that can turn off 60% of these neurons. That's a whopping effect. We got to think about it. We got to be careful. Because when there is epilepsy, there is more or less neurons active. When there is Alzheimer's disease, there are more or less neurons active. So you don't want to play with fire. But that's just one part of the story. What about those other 40%? Maybe they are fine. So here is the rat running in virtual world now. Same visual cues. So neurons are still firing. That's good news. And what you see is there is no map. It just goes all over the place. It's garbage. It's pretty bad. This is one neuron in the real world. This neuron is beautiful map, fires only in these two places, very little elsewhere. This is the same visual cue, virtual reality. There is no map. It's gone. You can quantify this with information content in the units of standard deviation and bits. It's a big effect between real world and virtual reality. And what I'm going to tell you very briefly is that even when some patients which come into the clinic and they want to figure out where the epileptic focus is, and at that time they show the virtual reality to patients, even in humans there seems to be very large deficit in number of neurons that are active. So I'm going to summarize this, that nearly 60% of neurons in hippocampus shut down in virtual reality. The spatial maps in hippocampus are quite corrupted in virtual reality. They are close to chance level, pretty much destroyed. So just the 40% which are active, they too are pretty bad. The hippocampus generates its own rhythm, which is actually quite precious for learning and memory. That rhythm too is destroyed in virtual reality in a big way, but I didn't tell you about it because we are out of time. Does this have any long-term adverse consequences? This half an hour, this circuit that I told you gets rewired with every word that you hear. We don't know yet. We are working on it to figure out long-term consequences. These are called longitudinal experiments. They are hard. We are working on this. What I want to do is to get you involved. What we want to do is to build the next generation of virtual reality where we can fully activate the brain and create decent neural maps. They don't have to be as good as the real world, but if they are decent, we are already there. But I believe that's possible. When we play with this timing at the level of millisecond between neurons, that's where the magic is. If we can make these maps memorable, you will have better and more memorable experience. You all know stories of people who are mnemonics, who remember lots of things. Whenever people remember a lot of things, they walk in a virtual landscape and associate memories to places. So that's the trick we are using. And that, I believe, in the long run can be used to use VR to even make us smarter. So that's the bottom line. So get involved and let's develop a VR that at least potentially is not harmful and maybe even better than what you might do otherwise. So thanks a lot.